Okay, so again, this is Amy. I'd like to welcome everybody again, and I have a couple special welcomes I'd like to say. If you are attending this webinar from outside of Minnesota, I want to welcome you. And also, if you are in the current Minnesota Numeracy Initiative cohort, I'd like to also welcome you. I'm glad that you all were able to be here. Okay, so I just want to start with sharing some objectives that we have for the webinar today. So it will be a 1 hour presentation by Andy and I, followed by a half hour of some more open discussion time where we can also do some guided practice questions. So during this hour and a half, we are hoping that you are able to deepen and broaden your knowledge of concepts related to ratios and proportional thinking. We're hoping that you could use the understanding that you already have of ratios and proportions and apply that to higher level applications of these concepts. And then, of course, we're also hoping that you are able to find some examples that you could use or adapt in your own classrooms. And so now I just want to talk for a moment about the CCRs. So the College and Career Readiness Standards for Adult Education, or CCRs, were released in 2013 and will be a driving force in the future of adult education. So they are identified as the skills and practices that learners will need for college and career success. And this full document is available online, and it's easy to find by searching. But I just wanted to mention the CCRs right now because we will be referring to these during the webinar, and I wanted you to just have this quick background. So we also will, we plan to refer to the mathematical practices, which are part of the CCRs, and you can see the 8 practices listed here, and these are just a list of practices that students should have opportunities to use in class in order to develop their mathematical thinking. So if you have questions as we go along, feel free to type them into the chat box, or you can jot them down. And so then Andy and I will try to answer along the way. Otherwise, we will address questions at the end during guided practice. Andy? So go ahead and you can take it from here to talk about ratios. And it seems like the PowerPoint is gone.
Okay, let's try that. I hit the wrong button. Can everybody hear me and see it now?
Yes, we can, Andy.
Okay, thank you, Rebecca. Okay, sorry, I just hit the wrong button when I tried to unmute myself. I'm going to talk a little bit about the ratios. This is something that we've worked with quite a bit, even back on the 2002 based GED test. So just a quick review. But we're going to highlight in this one the CCRS standard of 6RP1, which basically talks about using ratio language to describe a relationship. So when we think of ratio, we want to think of what are these things. So the ratio is just simply a relationship between two quantities. So some common examples where we might be able to see that would be something like if we're dealing with a little bit in the science test, this molecule that many people would be familiar with, that's H2O, which is, of course, water. Well, what does H2O mean? Well, it means there are 2 hydrogen atoms for every 1 oxygen atom, or a ratio of 2 to 1. So that's one that your students can kind of grab a hold of fairly easily. I did find another graphic that I thought was interesting in terms of ratio. And I'd like to take just a short chat question here. There is a problem with this graphic. There's something wrong in this graphic. can you find or do you see what is wrong in this graphic? And just go ahead and text it in if you think you know what we're talking about. Yeah, it's kind of hidden down in there. We'll wait just a little bit longer, then we'll go ahead and go. Okay, this was a graphic put out by the California Teachers Association talking about the teacher-to-student ratio in the state of California, which is 49th in the state, according to them, 49th in the United States. And they do a really nice graphic there showing that there are teachers and students in the classroom, but they say the teacher-to-student ratio is 20.9 to 1. Well, if we follow that logic for what they say for teacher-to-student ratio, that means there's 20.9 students, or sorry, 29 teachers to every one student. And that would be a phenomenal teacher-student ratio for us as far as being able to give personal attention, but it'd be really hard to finance. So really, when it says teacher-to-student ratio, it should not be 20.9 to 1, but it should be 1 to 20.9. In a ratio, we have to remember to show the idea that whatever we say first comes first. And that was highlighted here in the Mathematical Practice 6, the idea of attending to precision. Make sure that we're talking in a way that is accurate to our students. Yes, precision in vocabulary. And the second one they also got backwards, so we went ahead and fixed that one and said that nationally the teacher-to-student ratio is 1 to 15.4. So that gives an example of how to write a ratio when we're have words and we're building it up. And I like to use this example of the Metrodome, and I know the Metrodome doesn't exist anymore, but our students kind of still like talking about it. And in the Metrodome, if it was set up for the football configuration, it sits about 65,000 people. If we're looking at this picture, we can see that quite a few of the people in this area are wearing purple, of course, for the Vikings. So we're going to assume that 45,000 out of those 65,000 people are wearing purple. So our question might be, what is the ratio of people wearing purple in the Metrodome to people not wearing purple? If your students see this, is there something that you check on, yes, and I see Andrew's got it, that they might not catch? And that's the idea that they don't give you the non-purple numbers. The students are going to have to come up with that. So if we're looking for purple to non-purple, we're looking at Mathematical Practice 4. How do we model real-world situations with mathematics? Well, our purple number is the 45,000. They give us that. That's great. But the non-purple is the 65,000 to 45,000, which leaves us with just 20,000 people not wearing purple. And when we're done with the ratio, if possible, we should reduce it. Because trying to imagine or see 20,000 people, that's a lot of people. But if we divide both of those by 5,000, a common factor, we can see that there are 9 people wearing purple for every 4 people that are not wearing purple. So in ratios, just in the big picture, it's a relationship of 2 or more quantities. Most of the time we're only going to be dealing with 2, and on the GED test I think they're only going to deal with 2. And they could be written in 3 forms. We did the main first form there, the colon form, but they can also be written in fraction form and with the word 2 between them, relating that it doesn't have to be a part of a whole, it can just be 2 numbers. And lastly, the students do need to be able to reduce ratio values because some of the questions on the GED test will have the answer in reduced form, and they're going to have to be able to make sure they can catch the correct answer. So if we can do ratios, then sometimes we start hearing the word rate. So what is the difference between a rate and a ratio? They sound kind of the same. So what are rates? Well, they're just a relationship not necessarily just between two numbers, but between two measurements. So we're going to have some sort of real-world measurement involved in a rate. And they're often in unit form, and we're going to talk about unit form here in a minute. But they can be any relationship between two measurements. So here is a really, really busy slide, and you can all look this up back when we do a review if you want to watch this on the recording rather than trying to read it all. But these are some of the CCRs standards that talk about using a rate value, and we highlighted in green some of the things that we're going to do during this webinar, some of the skills that we're going to highlight. So I'm just going to do a few examples here that talk about the rates, and the first one was in that second CCRs standard, how to create and compare unit rates. So how do we create unit rates? Well, the first thing we have to have is some data to come from. So imagine you're going to your grocery store and you're going to buy some cereal, and my boys, they love the Captain Crunch, so I decided to kind of pick on those ones. But if you go to the grocery store and you're finding a cereal, you can often find it in multiple sizes at different price ranges. So here are 3 boxes, and yes, Andrew, we're going to look at the ounces. When we see this, the first box is 15 ounces, the second box is 22.4, can get 20% free, and the third box was 40 ounces because it was 2 bags inside that box. But within those ounces then we have different price ranges. So the first box cost us $2.50, the second box would be $3.35, a little bit more because there's more cereal there, and the 40 ounce was a little bit more expensive on $8.14, $8.14. So just in a quick little kind of chat poll here, I want you to tell me which of these do you think is the best buy? Which one of these would be the lowest cost per ounce? And we're going to give a few minutes for people to chat that. So go ahead and chat which box, the small, the medium, or the large box, which box do you think would be the best buy? Okay, thank you, Donna. Good, and Rebecca? Okay. Everybody's kind of coming up with the medium box, that middle box. Why is that? It's kind of hard to compare when you're talking about different values and different monies. So if we want to do this, the easiest way is to put them into values that we can compare a little bit easier. So if we pull those off to the side so we can get a little bit of room to work, we can see that it's $2.50 for every 15 ounces of the first box, and et cetera down through the rest. But if we reduce those values down to where the bottom number is 1, good. And yes, Shelley, the middle box is only 14.9, or about almost 15 cents for every ounce. The top box is 16, almost 17 cents an ounce. And that big box, which a lot of people will think, you know, hey, the biggest box, it must be the best value because we're buying the big stuff. That actually comes out to be the most expensive per ounce. So getting students to see that unit rate, and unit just meaning 1. So we're relating a cost to 1 ounce rather than multiples of ounces. So that was perfect. You guys did a great job on doing those comparisons. And of course, we have the least and greatest unit rates. So a second example that students want to be able to do is to show percentages as a rate per 100. And when we talk about percents, most people are, you know, I know we've done this a lot, but just to make sure we're all talking about the same thing. Percents is a composition word of 2 parts, the per being cut into or part of, and the cent being 100, the same way that a dollar can be cut into 100 pennies, so 100 cents. And we do this because if we use that 100, it's easier to get a value where we can compare values to each other rather than trying to go all the way down to 1. So we've got an example problem here. Find the percent when we have a rate per 100. And we're saying, what if in our class we had 8 out of our normal class, or our regularly attending class of 25, are out because they're sick with the flu, and gosh knows the flu is just nasty right now. So having 8 students out is not unheard of. So we want to ask what percent of the class is out. So if we're looking at what percent of the class, we have to relate how many people are out compared to the total class. Well, the 8 out of 25 does not give us a percent because it gives us a rate per 25. But if we are able to multiply both the top and bottom number in that rate, 8 people per 25 people, by 4, we'd see that that bottom number, the rate per 100 that we see, comes out to be 32. Therefore, 32% of the class is absent. And it's really nice for students to be able to see that, get a hold of it, and recognize it's not quite half, but it is definitely a significant percentage that are missing today. Okay, a third example is we need to be able to convert units when we're dealing with measurement. I was just doing this with my class today, and it can be a little tricky, especially for those students who may have grown up in a foreign country and are really used to those metric systems with the centimeters and meters and all that, to then throw in all of our wacky conversions in English. So we said, what if I've got a 3/4 ton pickup, and this does look like what I or my brother would do with a pickup, because we're going to make as few passes as possible to get all of our stuff moved. But how many pounds can that 3/4 ton pickup carry? So if we want to convert it, we need to think of multiplying by a conversion factor. So a conversion factor is just when we have 2 items that are equal, as Andrew pulled up there, and he's absolutely correct. There's 2,000 pounds for every 1 ton. So if I put those in ratio, 2,000 pounds divided by 1 ton, that's really a version of 1. And remembering that anytime we multiply any value, like 3/4, times 1, we get the exact same value. It'll just be in a different unit. And if we multiply those, we're going to come out that the tons are going to cancel, and you're going to be left with pounds. And this truck can carry 1,500 pounds in its bed, and I think he's probably overtaxing the back end of that truck. Okay, and our last example for the rates problems that we're talking about is to recognize that rates could be considered a slope of a graph. This is definitely a chunk that we expect to see on the GED test, so it's one with the coordinate grids that people should be comfortable with. So here we have Sue, a newly licensed driver. She's going to go out and get a car because she needs to get to work and stuff. She gets out onto Craigslist and found a 2001 Chevy Cavalier for $1,080. If you're willing to drive to Indiana, that is actually on sale, well, as of yesterday when I built this slide. So if you want to go buy a car, you can drive down to Indiana and buy that car. But Sue doesn't have that money. She needs to borrow that money from her dad. So her dad's going to go ahead and lend her the $1,080 to buy the car. But he's telling Sue she needs to pay that money back over 24 months. It's not going to charge her any interest. So how much does Sue have to pay back to her dad each month in order to pay that $10,080 off? Go ahead and chat that in if you can come up with that number. Okay, yep, we got some. Okay, so if we're looking at that, how do we come up with those values? Well, she's going to pay back $1,080, but do recognize, and this is a tricky one for some of our students, she's going to pay back $1,080, so it's actually going to end up being a negative $1,080 to her bank account. That's checks she's got to write out. and she's going to pay it back in 24 months, her change in time. And so the amount of money she's got to pay back every month is $45. And so we see that as a negative 45. And yes, we had the chats coming in at 45. That's excellent. But if we relate this back to a graph, we went ahead and graphed the value of how much she owes to her dad, starting at 0 months when she first borrows the money at $1,080 and going down to the $24 at the end. But if we look at her rate change here, in 6 months she's paid off $270, but that took her 6 months in order to do that. So if we look at that, that is a ratio, oh sorry, that animation didn't come up right, of $270 per 6 months, so a slope of negative $45 per month, $45 less that she owes every month. And that can then be converted into a linear equation of y equals mx plus b, slope being 45, and her initial condition, how much she owes at the beginning, of 1,080. And there's that rise over run out there at the end. So that's our setup for figuring out how do we do these rates as a slope on a graph.
Hey, Andy, can I add something before you move the slide? As I look at this, I'm just thinking that if we're trying to think about ways to increase the rigor of the work that our students are doing, what I see here, I hope that just to give you something to think about as you listen to this webinar, just by giving that first prompt about Dad lends $1,080 and Sue will pay it back over 24 months, if you just by giving your students that, then actually all these other components, if of course with scaffolding, your students can then build all of these other parts. So that's just something to keep in mind as you see all of these examples in the webinar today.
Yeah, absolutely. Having the students kind of go through and create this is really nice, especially when they start to see that rise over run, that the run or the rise is actually negative. You know, that she's paying part of the owed value off. Okay, and then Amy, you can go ahead and pick up for your next section of.
Okay, thanks, Andy. So again, just to add on to what I chimed in with before, you know, the question in my mind is how can we take these kind of the foundational ideas of ratios and proportions that I think that, you know, most of us are familiar with and our students have some familiarity with, but then how do we make those links up to those higher level concepts? So how can we do that for our students so that they're able to take their success with ratios and proportions and then be successful with the coordinate grid, the example that Andy just showed. Okay, so now let us move on to proportions. And so we'll start at the beginning just with a really quick review about proportions. I believe most of you are familiar with proportions. So here's a proportion. 1/5 equals 3/15. So a proportion is 2 equal ratios. A proportion is 2 equal fractions. And a proportion is a description of 2 quantities that change proportionally. So as that 1 changes into a 3 by being multiplied by 3, then similarly that 5 would change into a 15 by being multiplied by 3. And then another key element of proportions is that proportions have cross products that are equal. And so that's going to be a foundation for many other applications of proportions. So here's what I mean. The cross products are equal. So 5 times 3 will be equal then to 15 times 1. And that always is the case with proportions. Okay, and so building on that foundation, a proportion can be used to find a missing quantity when one pair is given and then the other pair has a missing part. So I'll do a quick example of that. So in the coffee shop that I manage, I know that I usually sell 3 muffins for every 10 cups of coffee that I sell. So I expect to sell 80 cups of coffee on Tuesday. So how many muffins should I order? So I think that's a realistic question that some of our students may encounter. So first, let's start by setting up a proportion. And you see I have an empty proportion there on the screen, and I actually recommend to students that they do that because it's like they're making a little, like a little worksheet for themselves, and then they can go in and fill in the pairs. So, so maybe one of your students would say, okay, well, I see a pair. I see that that 3 muffins goes with that 10 cups of coffee. That's a pair, and that's a pair that's given. And so then the other pair is going to have a missing part. And so I see that the number of muffins, that's the missing part, and to go with the 80 cups of coffee. So one of your students could approach it like this, and this is Andrew is agreeing with me in the chat box. So once we've set up the proportion, we can use what we know about cross products. So 10 times x is equal to 80 times 3. And so there's our equation, and the next step is just simply solve for x. So 10x equals 240, and then we can divide each side by 10, and then cancel, and x is equal to 24 muffins. So Andrew, I agree with you in the chat box. So a student could set up this proportion and then figure out that they would need to order 24 muffins that day. But then I just want to show a little twist to this, but maybe a different one of your students looks at this and says, you know, actually I disagree. You know, actually I see a pair, but that's not the pair that is given, that's different. I see a different pair. So the pair that I see is that I see the pair of cups of coffee. So 10 cups of coffee goes with 80 cups of coffee, and they're both coffee, and that's why they're a pair. And then, so then the corresponding pair would say that there are 3 muffins that I know of, but then that missing part is the X number of muffins. So that's the pair that has a missing part. And so this student is proposing this idea to your class. And so let's just take the next step. We'll go ahead and do the cross multiplication. And you can see that still we have the 10 times the x, and then also we have the 80 times the 3. So I just wanted to show this example to point out that there can be more than one way to organize the information of a proportion. It just has to be logically arranged so that things that actually are paired together actually do line up with each other. But there's more than one way. So be ready for this in your classes. Okay, so now that we kind of have this shared foundation in proportions, I want to talk about some examples of proportional reasoning, maybe at a more unfamiliar level for you. And so first, just to connect with the intuitive level of knowing math, you could do this example with your students. You could just start by asking the question, have you ever changed the size of an image on your smartphone or tablet? And that's a pretty familiar context, I think. So, you know, sometimes we have an image and it's kind of small and hard to see, so what we would do would be we would enlarge that, right? We would enlarge that image on our phone or on our tablet, and what happened was that when we do that enlarging, the length grows in a similar way to the way that the width grows. So they're growing in proportion. So the picture doesn't get stretched out, it doesn't get taller and thinner, it doesn't get wider and flatter, but the length and the width grow proportionally. So that's a real-life example, everyday example of proportional reasoning. So in general, I want to say the idea that proportional reasoning describes the rate at which something increases or decreases in relation to something else. So things are changing at the same time. And so the three examples that I want to share have to do with similar figures, with scale factor, and also the constant of proportionality. So let's start with similar figures. So I want to give you a chance to type into the chat box a little bit. So I'm going to ask a big open question. What do you notice? So please look at your screen, type in some things that you notice. And there, I don't even need to say this, there are many right answers. What do you notice here? So Beverly says the angles are the same. Andrew is seeing letters that are different. What else? Same angle measurements for corresponding angles. Okay, people are noticing that the angles match. What are the shapes that you see here? Larry's saying that the triangles are proportional. Both are right triangles. Thank you. Okay, good. So all of that is right. And so thank you for chatting in your ideas about what you notice on the screen here. So that is a activity that you could offer to your students as you start to talk about proportional reasoning. And then I also just want to add some vocabulary that could be helpful for your students to know as they're noticing what's happening with these two shapes. So you all were correct. These are the both of these shapes are right triangles, and one is smaller and one is larger. And I would say that they have the same measures of angles in each of the triangles. So to use I'll use these vocabulary words. So I could say triangle ABC is similar to triangle DEF because they are exactly the same shape. They're both right triangles, but they have different sizes. And then I could say that, for example, angle B is congruent to angle E, because it means they match exactly. It means they're the same. And then to use the word corresponding, I could say that, for example, side AC corresponds to side DF because both are the hypotenuse of the right triangle. So just I just wanted to point out the richness that could come to the discussion in your classroom just by introducing those three vocabulary words. And then again, this is pointing to mathematical practice number 6, which is attending to precision. So make sure that your students have the vocabulary to be able to have that rich conversation around similar figures. Okay, so let's do a little practice. First, look at the rectangles. Are they similar, yes or no? Chat your answer. Are the rectangles similar based on the definition that we just said? Are they similar? Are the rectangles similar? Yes or no? Go ahead and chat if you think those red rectangles are similar. Okay. I see some yeses. How do we know if we don't have the measurements of the sides? Excellent question. Okay, thank you for chatting your answers in. So people brought up a couple different things in trying to decide if they're similar. So actually these are similar because I made one by stretching out one of them. But that's actually a good point that you wouldn't know for sure without having the measurements. And so that is the symbol for showing that it's similar. So that is not on the GED test, but I just wanted to show you that so you could share that with your students if you cared to do that. So these rectangles are similar, and but the thing that I'm trying to illustrate with this slide is that shapes can be similar even if they're oriented differently on the page. So it does not have to do with how is it oriented. So one is rotated. One is rotated 90 degrees, and that's fine. So they're still similar, because I would say that the width of the larger rectangle corresponds with the short edge or the width of the smaller rectangle. So yes, they're similar. Okay, so how about this? Let's look at the triangles now. So with your best estimate, considering that you don't have the measurements, do those look similar to you? They appear similar. Very, very well said. I like it. Thank you for chatting in your answers. Okay, so yes, those are also similar, and I just, again, wanted to point out that they could be flipped around and oriented all different ways, and so have your students watch for that. But then they're still similar. And then this activity made me think of mathematical practice number 3, which is to construct viable arguments and critique the reasoning of others. So I just think if you were to offer questions like this to your students and then have them defend their position, like why is this similar, why would you say this is similar, or why is it not similar, would be a really valuable activity. Okay, so one application of proportional reasoning is to find the length of missing sides of similar figures. Okay, so now here is the information that was missing. So if I tell you that these are similar by that symbol, and then you have these measurements, then you are able to use the corresponding, you're able to use pairs that are built from corresponding sides to create your proportion. So when I look at this, the short side on the first rectangle is 3 feet, and the short side on the second rectangle is 1 foot. So to me, that's a pair that I see. Those correspond, so 3 goes with 1. In a similar way, that 6 would go with X. And so there's my proportion. And so then we can just solve this in order to solve for X. So to use cross multiplication, 3x equals 6, or then x equals 2. So that is one way that your students will come across proportional reasoning. Okay, so now I'd like to share a second example of an application of proportional reasoning, and so this one is about scale factors. And this standard that you see written on the slide is, this is actually from the GED Most Missed Questions, the handout that they've sent out recently. So I included this because it's a most missed topic on the GED test. Okay, so let's look at this example here. I'm thinking that this is probably like in a museum where they do a lot of shipping, and what they have to work with is that they have this model of a type of, like the dimensions of a box that normally work for them, and what they're able to do then is scale that box larger or smaller based on the item that they need to ship. And so so we're given the model and its dimensions, and then we're given the picture of the crate and some of its dimensions. And so when building the crate from the model, what scale factor was used? Another way to consider that is to just ask the question, what were each of the model measurements multiplied by in order to make the crate? So, so now I think it just becomes much more evident of what to do. So we know that division is the opposite of multiplication. So if we're asking what was it multiplied by, you just can go back and divide. So I'm looking for a pair where I know both, and one that stands out is I see we have the lengths, those longest sides of the model and of the packing crate. So we can just divide the lengths. So as we're trying to find the scale factor, let's we can divide the lengths, and then we can come out with a scale factor of 24.5. Okay, and now just because I really want to make sure that I'm understanding this correctly, I wonder if I can check this in a different way. So I'm looking for another pair where I'm given both, and it looks like the height is available for both the model and on the packing crate. So if we divide the heights, then we also will come up with a scale factor of 24.5. So this makes me satisfied that we have determined that the scale factor from moving from the model to the packing crate is 24.5. So that might be the question. What is the scale factor? But then an additional question that your students might see is that if you have a scale factor of 24.5, then let's use that to find the missing width of the packing crate. So now that we know what the scale factor is, could you all chat this answer? Now that you know the scale factor, now that you know the relationship between the model and the packing crate, what is the new width of the packing crate? I see a 49. All right, there seems to be a consensus, and I agree that 49 centimeters would be that length. So again, so I just kind of want to pause here and look at the big picture. So what I'm talking about and what Andy was talking about, these are all ways to just talk about how things are growing in a similar way or shrinking in a similar way. If you were going from the packing crate and then making the model, right, they would be shrinking similarly. Okay, so now I want to, for my final example, I want to talk about applying proportional reasoning to the constant of proportionality. So, and then the equation that goes with this is that y equals kx equation, and that is the equation showing direct variation. And so the reason that I thought it would be important to include this, this example and to include a discussion of this topic is that I remember this from when I took a GED Ready practice test, and this was on there, and they specifically had the equation with the K in it, so I just wanted to make sure that we talked about this a little bit higher level concept when we talk about proportions. Okay, so to start about discussing the constant of proportionality, it has everything to do with this equation. So this, again, is the equation that shows direct variation. So this looks like algebra, so let's break it down and just see what it is that we're talking about. So x in this equation just means an x value or an input. And then the y in this equation just means a y value or an output. And then K stands for the constant of proportionality, or another way to say that is the ratio of y to x. Okay, so that idea that the constant of proportionality is the ratio of y to x, I'd like to explore that a little bit because it's like a little much to absorb all at once, I think. So let's just talk about y. So if you start with the y equals kx, let's just use what we know about algebra to rearrange this into a helpful form. So we know from algebra that it is fine to just switch what's on each side of the equal sign. So we're just switching it to kx equals y. Okay, then also using the rules of algebra, it's fine to divide each side of an equation by the same thing. So let's divide each side by x, and then you'll see that the x's will cancel. And so what we're left with is k is equal to y over x, or the constant of proportionality is the ratio of y to x. So that's how all of these pieces fit together. Okay, so let's take it from that very abstract idea and now look at a geometry connection. So here's a very familiar application of the constant of proportionality. So the question that I'm asking here is, when comparing the circumference and diameter of a circle, what is the constant of proportionality? So I wonder if a couple people could chat this. We're talking about circumference and diameter and the way that they're related. So what's the formula? What's the very simple formula that is familiar that shows how that circumference and diameter are related? How do you relate the circumference and a diameter in a circle? Okay, Marty's saying it seems similar to slope and y-intercept equation in disguise. I think that I agree with you, and I'm going to show that in the example. And I'm glad you noticed that, Marty, because, you know, again, I think as ABE teachers, the more we can show things as just many or just like one concept that we're looking at from multiple perspectives rather than like all these different things that people need to learn. Okay, C equals pi d. Thank you, Rebecca. So let me put that on the screen for you. Okay, C equals pi d. So we are talking about relating diameter and circumference, and this is the very familiar way that we've been doing that we know how to do that. That's on the formula sheet. C equals pi d. And so I just want to put that right beside the y equals kx equation. So if you were to say these in words, you could say, in order to find the circumference of a circle, you would multiply its diameter times pi. Or I could say, in order to find the y value, I would multiply the x value times k, right? So just make this easy link of connecting the pi to the k in these two equations. And so in this case, the constant of proportionality, or k, is pi. Okay, so just kind of like we did in the previous example, once you've found what that constant is, then you can use it to find other missing pieces. So look, I put up a new diameter. So if we know that the diameter of a new circle is 25 meters, and then we know that it's the constant of proportionality is pi, then and just use 3.14 for pi, what would the circumference be? Can you all quickly do that on your calculator? What would the circumference be for a 25-meter diameter circle? Okay, thank you, Anita. Let's see. So I'm seeing 78.5. And I agree, 78.5. Okay, so that's just one way to find the constant of proportionality in a very familiar example, and then how to apply it. Okay, so now let's look at something that looks a little bit more like a GED question. So To me, I see a lot of words, and I see a coordinate grid and a graph, and so this looks like a GED question to me. In this graph used by a development company showing the relationship between the number of houses being built and the number of framers that they will need. Find K, the constant of proportionality. So maybe this would be a graph that would be used by the scheduler to try to organize the workflow for the week. So just take a minute and look at this graph. And then the question is asking us to find K, the constant of proportionality. So, just start with the equation so we can kind of have a starting place. And then we know that you could rearrange this equation then to make K equals Y over X, or the constant of proportionality is the ratio of Y to X. So in the graph, we are looking at all of the points, and so in order to look more closely at it, let's look at some specific points. So here, I'm just going to choose a couple points. I'll choose 2 points that are on the line, and I tell my students, choose points that are easy to work with, that show up right where the grid crosses each other. So there's 2 points. Let's look at what they are. So the lower point on your screen is 4, 20, where X is 4 and Y is 20. And then the upper point is 10, 50, or where X is 10 and Y is 50. So so again, to find K, we're looking at the ratio of Y to X, or Y divided by X. So let's just do that right here for each of these points. So Y divided by X is 20 divided by 4, which is 5. And then, or also you could say 50 divided by 10, which is 5. And so the constant of proportionality in this situation is 5. K equals 5. And it looks like everyone who chatted in already had figured that answer out. So good. So here's how the constant of proportionality is applied in a situation like this. And now I just want to re-emphasize the point that someone made earlier about the connection to Y equals mx plus b. What if you instead approach the same question as a YMXB, Y equals mx plus b type of situation? So that's the equation of a line. And so if we are seeing it as the equation of a line, let's fill in the parts that are missing. So I put in the rise and the run using those 2 points that I have on the line. And so now I'm able to find M equals rise over run, which is 30 over 6, which is 5, that same 5 that we already found. And so if we substitute all of the pieces into the equation for the line, we have Y equals the 5 substituted for the M, and then plus 0, because the 0 substituted for the B, because B is the y-intercept. Where does your line cross the y-axis? And it crosses at 0. So y equals 5x plus 0, or to simplify it, just y equals 5x. So we can just make this link about how the constant of proportionality is the same as the slope in a situation like this.
Okay, so I'm going to come in and just remind us that we are in the E-quip episode season 2 for our webinars that we're doing. Remember that any of these, including this one, are available up on the Atlas site for viewing once they've been done. So episode 4, 5, and 6 are coming up. Episode 4, the registration for that should be up and available right now. So if you've got an interest in doing the next webinar, it is coming up in January on the 14th from 3:30 to 5, and you can go ahead and register for that. This episode and any of the ones previous, look on the Atlas site, and including season 1 is up there as well. Do note that this is not the end of our webinar. This is going to be the end of our recorded presentation, and we are going to have a question and answer kind of session here at the end. So again here, remember to register for episode 4 coming up with Abby Rosa, Kristen Knudsen, and Amy, and they're going to be right online with this complex geometry, which can be a little bit more rigorous than it was on the old test, just to get us up and make sure that everybody's comfortable with the new materials. So now time for question and guided